Oh, okay, guys. We are now in this lesson 4, part C of the serial dilution. To the first dilution. From the first dilution, you move to the second dilution. From the second dilution, you move to the third and the fourth. And finally, from here, you move into your culture plate. You culture plate to understand the number of colonies. From there, you can be able to determine the microbial concentration of the unknown or unstandardized solution. Having said that, in any serial dilution, the basic principle of in any serial dilution is for you to maintain the index of your dilution factor in base 10, or should be in base 10. Whatever you do from the inoculant to the diluent should be a total of base 10, so that your dilution factor will be in base 10. So once you move 1 ml from here, it must join into another diluent that must result into a base of 10. That is the first basic principle you should have in mind. So if I move 1 ml from the stock solution from dilution, if I move 1 ml into 9, I will have 1, the sample you are adding, over into the diluent. So that diluent plus the volume you added, total volume will be 10. So the dilution factor for A is 1/10. Then when you move, shake, agitate properly, take 1 ml from this test tube A into test tube B, 1 ml into 9 ml. That should give you 1/9/10. That should also give you a dilution factor of 1/10. The same thing is done for C, 1/10. The same thing is done for D, 1/10. Then the final volume is what we call the inoculum. This refers to the inoculum, the final volume in which you use to culture in your plate, either by streaking method or by populating method, whichever way that is appropriate for your analysis or for your microbial count must be done. Take note of this final volume, which is the inoculum. So once you put it there, you have your number of counting, so that if you incubate at 37 degrees Celsius or whatever temperature that is appropriate, you could have the valid microbial colony in your culture plate. Having said that, then let's move into the main business of the day. The essence is for you to have a dilution factor of 1/10, 1/10, 1/10. That is in fractional level. When you now change it to standard form, this fractional level 1/10 will result to 10 raised to the power minus 1, minus 1, minus 1, minus 1. What this means is that the individual dilution factor, that is IDF for test tube A, IDF A is equal to 10 raised to the power minus 1. For B is the same thing. For C is the same thing. For D is the same thing. There are some cases where I will change this dilution factor, where if I have 0.1 in this one plus this 0.1, I will need to add it into 9.9, so that at the end of the day I will have 0.1 over 9.9, 9.9 plus 0.1. That will result to 0.1/10. And this 0.1/10, if I want to reduce it further, this 0.1 is equivalent to 1/100. And this 100, when I change the dilution factor now, that will be 1, that is 10 raised to the power minus 2. So it does not mean that it must be, but basic calculation, you must have to assume for your elementary understanding, you are taking only 1/10, 1/10. There are some textbooks and some calculation that will go beyond 1/10, 10 raised to the power minus 2 or minus 3. So we have taken for all these ones, since you have 1/10, 1/10, all of them we did this. So if I change the dilution factor, I must change this in order to balance, to have a dilution factor in base 10. So that is the trick you must also learn. Then that is another thing, you should be able to calculate the dilution factor for every test tube in your dilution method. This is how you get it. Then the total dilution factor is total dilution factor after the series of serial dilution that you have taken place. For total dilution factor A, since it's only one dilution factor that was done, 1 into 9, the total dilution factor TDF is the same thing as IDF. But for test tube B, TDF is 10 raised to the power minus 2, IDF is 10 raised to the power minus 1. C is 10 raised to the power 3 because you have added 1, 2, 3. The 4 is 10 raised to the power minus 4. 1, 2, 4. So the one you use for inoculum, once you use this one for inoculum, it will take the final dilution factor of the test tube where you collected your inoculum to culture on the plate. That will be your dilution factor when you are calculating your microbial count. So let's basically define the equations. The equation is volume asterisk, that is final inoculum volume, which we have discussed here. Take note of this, it's very important in the equation. You have IDF, total individual dilution factor, we have explained it. You have the other one, total dilution factor, we have explained it, and it is always calculated. IDF is also calculated by saying inoculum volume over diluting volume plus inoculum volume, which I already discussed. That will give you the dilution factor, and the dilution factor must be prepared to have index base of 10, that is 10 raised to the power minus 1 or minus 2 or minus 3, as the case may be. Microbial concentration equals to cell concentration, which is also equal to number of colony divided by TDF of the one you use for inoculum volume times the inoculum volume. That is the equation that we are going to use. You go to exercise 5, there you have the question. Then let's go into solution and see how we approach the question. All questions is based on this equation 1 only. Then you now go to the equation 1, you now say it is supposed to be equation, then okay, equation 2 for dilution factor, dilution calculation and microbial enumeration, we now say number of colony divided by TDF times inoculum volume of inoculum. Then we now say number of colonies that was given in the question is 45. Cleared. The volume of inoculum that was used is 1 ml. What is the total TDF? TDF is also given. Total dilution factor is also given. 0.000001 is equivalent to 1 times 10 raised to the power minus 6, which is approximately the same thing as 10 raised to the power minus 6. So therefore, the microbial load, that is the microbial concentration here, is ml is equals to 45 divided by 10 raised to the power minus 6 times 1. When you do the calculation arithmetic, the equation will now be 45 times 10 raised to the power 6. And when you convert it to standard form of microbial counting unit, it becomes 4.5 times 10 raised to the power 7 CFU per mil. This is your answer to question 1. Say calculate the estimated number of microbial cell per mil, that is concentration now, in the original sample. You are done with question 1. Then question B of the exercise 5 says, if 150 colonies were observed in the culture plate now, determine the microbial load or concentration of the stock solution. Then let's go to solving this question and say, if 150 was found, no longer 45, you say the microbial colony is 45, the volume of inoculum is 1, TDF is still the same thing, nothing changed in TDF. Let's see if the answer will change. You say 150 cell was observed, divided by TDF 10 raised to the power minus 6 times 1 equals to 150 times 10 raised to the power 6. When you multiply it and change to standard form of unit, microbial unit measurement, you now have 1.5 times 10 raised to the power 8 CFU per mil. That means almost some number more than 100 has been added to this. Okay, yeah, a million is some thousands, 100,000 has been added. So let's quickly, that's the answer to this one. We are done with this question. Then we now go into exercise 6. You have another chart in this exercise 6. This is a diagram. You have a stock culture of that was serially diluted 2 times and inoculated in 2 different plates, culture plates. Now let's take the question. If the stock solution, using the diagram above, if the stock culture have a microbial load of unknown concentration, using the diagram above to determine A, the volume of M, that is number of colony in plate, B, the microbial load concentration of the stock solution. So now basically we are looking for the number of colony in this culture plate M, which is not given. You may know every other thing, but you don't know the culture plate, so we can now use this equation to try and find out. But the trick of the question now is that there's another inoculation that was done with a reduced volume of inoculum. This was done with 0.1 from the same culture, from the same test tube, dilution factor. This was used 1 ml or no concentration, but when we use 0.1, we found out that the number of colony is 10. Therefore, if the 10 is in 0.1 volume that was assessed, how many colonies will you likely observe when you use 1 ml of the inoculum into this plate? That will give you n. For you to do that, you say number of colony is a direct function of the volume of inoculum. That is why I say take note of volume of inoculum. Number of colony that you observe in a plate is a direct function, is directly proportional to the volume of inoculum from the same test tube. So if you are diluting it, it will get lower. The higher the volume, the higher the colony. The lower the volume, the lower the colony you are likely to observe. You say therefore if 0.1 ml is equivalent to 10 colonies, therefore 1 ml will be equivalent to m. You make n subject formula 0.1 times m times 10 times 1. You divide both sides by 0.1, 0.1. You have 10 divided by 0.1. That will give you equals to 100. Therefore, m in that culture plate from the diagram is equal to 100 colonies that will be observed in the culture plate. When you inoculate 1 ml of this test tube B into a culture plate called M, you will likely see 100 colonies observed. That is the calculation aspect of it. Then the B question now says, what is the microbial concentration of the stock solution? We say microbial concentration of the stock solution. So what is the ml of this stock solution? Then you move down to your normal equation of saying microbial load concentration is unknown. Number of colony that you are using, this one is already 10. The volume that is in use for the inoculation is 0.1. Then you must note something. Each time you use a plate, each plate must be the same with the inoculum used. When you are using 0.1, you must use its own number of colonies observed. When you want to use this second one that was determined, 0.1 ml, you will use 100 colonies. Note, use only the one that is provided, not the one that you calculated. Having said that, then let's quickly move down to total dilution factor. Total dilution factor was not given, but it was given a diagram. From the diagram, you will know that you have 1 ml into 9 ml. That will give you 0.1. You have another 1 ml into another 9 ml. That will give you another 0.1. So when you multiply the two, 0.1, you now have 1 over 100, which is equivalent to 10 raised to the power minus 2. So you have determined your total dilution factor. Then you now move to the final process of now calculating the ml. The ml microbial concentration is number of colony divided by TDF times volume. While the number of colony we are using is 10, the dilution factor is 10 raised to the power minus 2, and the inoculation volume is 0.1. So when you do the mathematical calculation, it will be equivalent to 10 divided by 10 raised to the power minus 2 times 10 raised to the power minus 1. Then when you simplify it further, it will be 10 divided by 10 raised to the power minus 3, which is equivalent to, when you now transpose this one into removing the negative index upwards and remove the division, 2 will cancel each other. It will come up and say 10 times 10 raised to the power minus 3. 10 times 10 raised to the power 3. That will be equivalent to, total will be give you 10 raised to the power 4. So when you now change it to standard form of microbial unit measurement, it will be 1.0 times 10 raised to the power 4 CFU per ml. This is your answer. Thank you as we move to the next lecture.